transistor. It has base collector, base emitter. We have to see which one is which. We've got to check the diagram. One is base, the other one is emitter. And if you are wondering where is the third one as the collector, this case is the collector itself, that one. So when you're screwing that device to a heatsink, which is a flat metal with lots of fins, the case becomes the third electron collector. So some of the devices have two-terminal transistors, two-terminal. The case is the hot, and it can be collector. There are some others, like this transistor here. This is a medium power transistor. One is base collector emitter, one of the three. So you've got to sort it out from the data sheet. But it also has a metal stud, metal casing, which the semiconductor is attached to that metal casing for heat conductivity. So as the junction hits, it transfers the heat to this stub, this metal stub that you can see with a hole in there. And then when you install that on a flat surface like that, right there in the middle of it, this additional area that you can see, this is a hollow, just metal basically. When you attach it there, the heat transfers from the stud into the metal and radiates into the air. So it makes the heat transfer higher from the whole thing with the stud, with the casing or heat sink into the air, as opposed to the metal alone by itself, because of the exposed area. So the trick is this: when metal contacts metal, the heat transfer from metal 1 to metal 2 is immediate. You take copper, you take iron, put them together firm, screw them together firm. Almost, you can say, at the interface of the two, iron and the copper will have the same temperature. So there is no temperature gradient between the two, metal to metal. So when the case of a transistor contacts that external metal, the case of the transistor has the same temperature as the metal itself, known as sink temperature or case temperature. The junction, when it contacts the case internally that we don't see, it's inside, it does have a little bit of thermal resistance. In other words, the junction temperature will be inside the device will be a little higher than the case temperature. So we have to be aware of that fact. Usually, you can't do anything about that internal heat transfer resistance because it's built into the device. Now, today's topic is when you're buying a transistor such as that transistor, which says 150 watt. They can dissipate up to 150 watt. We want to know how much power can we dissipate in this when this transistor is incorporated, say, as part of a power supply. In the previous example, the review number 1, if you recall, I showed you a voltage regulator. I showed you a transistor buffer in the output. And I showed you that the collector voltage is about 10, 11 volt. Emitter voltage is about 5 or so. So there was around 5, 6 volt drop between VCE, and it was handling half an amp. It was delivering 500 milliamp at the emitter. Say the collector is also 500 milliamp, half an amp. So half an amp times 6 volt, that's for VCE, makes it 3 watt. So that transistor was dissipating 3 watt. But the question is, Can we just put a 3-watt transistor there and hope it will function? The answer is no, not quite, because when you dissipate 3 watt in a transistor of that small size, its temperature will rise quite high, and therefore its power handling capability will decrease. Whatever manufacturer says Pmax is, let's say, 5 watt, that Pmax is subject to a standard temperature. So here it is. Topic number 1 in the power transistor is this curve, which you have it in page 1. It's called power derating curve. The manufacturer will specify what is the transistor rating. For example, this transistor, its Pmax is about, I think, 150, but let's take it for 100. Condition: you can keep the case temperature at 25 degrees of Celsius while it is dissipating that maximum, say 100 watt. So if your case temperature is kept at 0, fine, it will function with 100% reliability. If the temperature of that case rises to up to 25 degrees, you are in the border. Theoretically, it can hold that 100 watt burden dissipation. But if your temperature rises because of the circuit application beyond 100, then don't count on that 100 watt permitted power, because the transistor can technically say burn. It can fail due to the rising internal junction temperature. So manufacturers usually, when they sell you a transistor, they will have a section, it's called power derating curve. It's not a curve, it's 2 straight line approximations. They will tell you what is the Pmax. The standard is up to 25. So it's a kind of universal standard. 10 watt transistor means 10 watt is good up to 25 degrees Celsius. But past that point, you have to see how good is that transistor. Some will have very small Kp, or coefficient, derating coefficient. Some will be larger. In other words, some will lose the ability to dissipate very rapidly with rising temperature. Some will sustain longer. I bet the one that can take a higher temperature, more expensive. It should be. So you need to know the slope of that line so you can predict what will be your operating temperature and how much power you can expect to dissipate in it. You can burden as a dissipation, as part of a maybe application. So here I gave you an example. Let's say the power derating coefficient Kp, which is measured in the units of watts per degrees of Cs. This is the amount that you have to deduct per every degrees of Cs as you step beyond the 25 degrees. For example, if you go to 26 degrees, you don't have now 100, but you have 1 degrees of C's increment multiplied by the derating coefficient, whatever that might be. Here's an example. I gave you a curve with a derating coefficient of minus 0.8 watts per degrees of C's, derating coefficient. So we are using that transistor. It's a 100 watt transistor. Pmax is 100 watt. Okay, for less than 25 degrees of C's. So we're using in an application where the temperature T case can go up to 50 degrees of C. This is the maximum tolerable temperature. The maximum that it can tolerate is 50 degrees of C. So we are marking that one, 50 degrees of C. Okay. We want to see what will be the handling power, how much it can take as its maximum. So very simple, it's the rating. So P dissipation is going to be equal to, you will take the 100 watt, which is the given at 25, and then you will deduct delta C, which is 50 degrees of C, from 25 degrees of C, that's the reference, multiplied by the multiplied by Kp, 0.8 watts per degrees of C. This is the K. Work this out, and of course, 80 watts. That's it. This transistor can only stand to 80 watt dissipation if the case temperature is going to rise to 50 degrees of Celsius. Let's see, how much is 50 degrees of Celsius? 50 over 100 times 180 plus 32. That's 122 Fahrenheit. 122 Fahrenheit, almost half boiling point. That's a pretty hot, temperature. You can touch it like half a second, feel it, but it won't sizzle. It's just hot. Well, I say the equipment, whatever you're making, do expect that it should be tolerable to a momentarily touch. It should be tolerable. That's the maximum you can expect. If you allow the dissipation or case temperature, whatever this is calculating for you, if you allow to exceed 80 watt while your case temperature is 50 degrees, then it's prone to fail. The transistor can fail. There is no guarantee. So don't surprise if you're buying a transistor for 100 watt, it can tolerate 100 watt. That 100 watt pertains to no more than 25 degrees of Celsius. If it's going to rise to that temperature, say stay steady at that temperature, if it stays steady at that temperature, then you have only an 80 watt transistor on hand for that application. You don't have that 100 watts. But what will happen is this. Transistor on its own, say this transistor here, if I dissipate 80 watt of power, say 8 volt and 10 ampere, if it conducts VC equal to 8 volt and the current of up to 10 ampere, that adds up to an 80 watt. That is, of course, under this rating, 100 watt, but this case temperature, I'm 100% sure at that rating will be way, way higher. It won't be able to sustain, because the temperature, as you put that much power in it, will keep shooting up. It will go quickly to 50 in 2 seconds, and then in another 2 seconds, it will go to 100 Celsius, 150, 200, 250, 300. By then, it will fail. So how can we put a limit on that maximum temperature? Or why does the temperature rise when power dissipates? Well, the law of thermodynamics. If you have a closed system, this is a closed system, and you keep putting energy, joules per second, power is joule per second. You keep putting joules by time, your energy is building up in the system. When energy builds in the system, if it is not doing external work, laws of the thermodynamic, it will accumulate in the system, the energy of the system. As the energy goes up in a solid, that means kinetic energy will go up, the material temperature will go up by definition. So that's it, you keep putting there, energy will keep going up. Only a little of that energy will be lost with this tiny little surface of it into the air. But how can we enhance the transfer from that body into the air? It's the one that I just told you. Two metals contacting each other. So we'll take this material, this transistor. Look, the bottom is flat, deliberately it's made flat. And we will install it on a plate, preferably, as far as weight is concerned, for an aluminum plate. We will install. So we have to drill holes so that the pins will go through, and then we have to isolate the body from that plate, because the plate is electrical conductor. This is collector. If you install there, the whole body becomes a collector, which sometimes we would love to do that. We put a screw on the top of that metal and it will become the collector bead. So you've got to install this so that the heat of joules per second that is fed into the transistor junction will transfer to the case will transfer to the metal, and the metal will transfer to the air. Such a base metal is called heat sink. So the picture of a heat sink, I tried to hand sketch right here, and situation of the transistor being installed in it and two wires coming out of it. Okay, so there's a firm contact between the transistor and the flat part of that heat sink. The rest are fins, blades, which is installed on the flat plate. Actually, it is cast initially together. The more are this number of the plates, the better. It will transfer the heat to the air, and it will keep the sink cooler, closer to the air temperature, known as the ambient temperature. So we have an ambient temperature, that's room temperature. And we're assuming as we are dumping into the room temperature, say, doesn't change. It stays nearly 20-25 degrees. So as the sink temperature rises above the room temperature, the heat will transfer from the fins by convection, airflow, into the room, and eventually at steady state, it will reach an equilibrium temperature. And we are hoping, and we have to design in a way that that equilibrium temperature will be our computed operating case temperature under the load. So if it is dissipating 50 watt in this example for the transistor, the sink temperature is planned to be not exceeding 50 degrees of Celsius. So how do we go about the designing of the sinks? So sinks are passive metals, basically. They must have a flat part. So let me erase this board, give you a hand sketch. If you Google the heat sink, please do that so that you will get a better picture, like the actual heat sink. I don't have any with me. We have it at school, but not at home. So this is what it is. I'll just draw a few. It is initially a base plate, approximately 2 millimeter thick, and then you have fins installed on it. It's very difficult to give that picture in 3D. So let me see if I can just put two fins here and there. Okay, so I'll erase this part and then getting it into a 3D perspective. And they should go down like that, down like this. But almost it tells you here, and then we have, of course, a background. Lines that you can see. One more here. Okay. This is, why did I put that here actually? It should go from here. Okay, this is the best I could do. Of course, it came out to be asymmetrical. I was intending to make that side identical. That is a three-dimensional, so-called the three-dimensional picture. Of course. Actually, there's a corner here. Okay, does that help visualization a little bit? So we've got,
it does look familiar.
It's kind of a 3D perspective of it. But we've got many of these fins. So the more are the number of the fins, and the deeper or longer is the sink, or the base, you've got more ability to transfer the heat from the case into the air. So this is called T of the case, and this is TA, air temperature. This is case or sink. We take both of them approximately the same for the reason that I explained. The reason is the casing of that transistor, when it touches the sink, it's installed on the sink through the holes, of course. It practically makes the case temperature and the sink temperature nearly identical. There's also a gradient, but nearly identical. So power, as it enters into the sink. So this is the transistor here, sitting on it firmly. As the PD, dissipated power in transistor, we're assuming that all of that power dissipated by the transistor transfers into the sink. Of course, a little part of it, very small part of it, will go into air. Well, it's just like a high resistance, low resistance. Heat always prefers to travel through the most conductive path as opposed to the higher conductive path, high resistance path. So the heat will transfer to the sink will give that energy back into the air, and at steady state, the following will apply. T of the S minus T of the A, the temperature difference between the sink. I call that TC minus TA will be equal to a coefficient known as theta SA times the P, D. So the temperature difference between sink and air, or the transistor and the air, will be proportional to the power being dissipated in the sink or delivered to the sink. Theta SA is called thermal resistance. Theta SA, known as the thermal resistance of the heat sink. You buy that. The unit of that one is degrees of C's per watt. Degrees of C's per watt, which should match the equation, because on this side of the equation you have degrees of C's, on this side you have watt, this is degrees of C's. So the unit of thermal resistance should be degrees of C's per watt. So when you multiply, it just leaves C's matching the C's. So theta SA depends upon a total area, total sink area, multiplied by F, air flow. Okay, so let's see what that is. If you have no facility to move the heat away from the blades, in other words, just standing by itself with no fan, given F, and the given area for a heat sink, you've got a given amount for theta SA. Theta SA. Now, which one is better? If theta SA approaches towards the zero, theta SA approaches towards zero, it means no matter how much heat you're putting into it, it's keeping it same temperature as the air temperature. So if the room temperature is 25 and you're dissipating, say, that maximum 100 watt, that's it. It just takes the 100 watt and puts it into the air because it keeps